Okay, just as a reminder, Lunar-VISE is the Lunar Vulcan Imaging and Spectroscopy Explorer. This was an instrument suite that was selected last year in the PRISM 2 call, and it was selected to go specifically to the Gruithuisen domes, which we see here in this image. So our 10-day surface investigation is part of what you've heard about already this morning, which is CLIPS task order CP21. Okay, so our overarching science goal is really to understand the composition and rock type of these unique silicic domes, and to really understand how we can then apply what we've learned at Gruithuisen to all the other silicic areas across the lunar surface. And we're going to do that by first mapping local variations in composition. When we talk about composition, we're talking about silicate composition as well as thorium abundance. And we want to relate those compositions to rock and regolith properties, surface features, and dome morphology. And then obviously, since we have in situ measurements at the surface of the domes, we want to take any variations that we see and place them into the context of what we have from all the orbital remote sensing data that we have. Because obviously we have a plethora of data. Sorry about that. And then we also have an exploration goal, and that's to really understand the geotechnical properties of the regolith. From remote sensing observations, there's some suggestion that perhaps the regolith or the rocks composing the dome have a unique thermophysical nature. And so we're there to characterize that, and then also understand and characterize how the rover and the lander also alter or impact the regolith properties. Okay, so our instrument suite includes instruments on a lander and a rover. And I apologize in advance, we don't have a lander or a rover yet, so you'll have to see our schematics, or very simplistic schematics here. Our lander suite includes two cameras, a context camera that's on top of the lander, and then we also have a descent camera that will be located at the bottom of the lander looking at the surface. And so we'll be using both of these cameras to really characterize the geologic landing site, but then also look at any plume interactions. And so between both of those cameras, we should get an understanding of both the in situ regolith behavior and then also how that regolith is altered from the lander and the rover. On our rover, we have two main instruments, or three main instruments. We have two multispectral cameras that are sitting on top of the rover. These are LV-VIC and LV-Cirrus. And we also have a gamma ray and neutron spectrometer that's situated on the opposite end of the rover itself. If we assume that this rover is approximately 1 meter in height, when we think about the spatial resolutions that we can get from our multispectral cameras, you can see here on this table that at about 3.6 meters from the rover, we should be getting sub-centimeter spatial resolutions. And if we go out to 100 meters, we're still talking about tens of centimeters at the thermal infrared wavelengths and centimeters in scale at the visible near infrared wavelengths. So as I said, on the rover, we have our two multispectral cameras. Those two multispectral cameras, the LV-VIC, which is at visible near infrared wavelengths, and LV-Cirrus, which is at thermal infrared wavelengths, are co-located in a single enclosure, which we can see here on the left. That allows them to be bore-sided to one another, and it allows them to make panoramic scans together with one another. The visible near infrared camera, LV-VIC, has 7 spectral channels, which you can see here on the right. Those 7 spectral channels have been chosen specifically to be similar to spectral channels that we've seen on Clementine, El Rock-Wack, and Kaguya, which again allows us to take our in situ surface measurements and compare those to the orbital data sets, which will really be key for ground truthing that data set. We also will use these spectral channels to look for any mafic mineralogy across the domes. And so this will give us an understanding of the iron abundance across the domes. LV Cirrus has 4 channels, 3 spectral channels at 7.3, 7.5, and 7.8 microns, and then also a wide range thermal infrared channel. And so these three spectral channels will be used to map silicate composition. And we've chosen these 3 bands specifically to be at shorter wavelengths to allow us to discriminate between silicic material compositions. These channels were also chosen to overlap with orbital data sets like Diviner and Lunar Trailblazer. And then we also have some overlap with the L-Cirrus instrument that will be going to the south pole of the moon as part of CP22. And really the driving thing for the thermal infrared system is to, again, map silicate composition, but also use the wide range thermal channel to understand the thermal physical properties of the domes. Okay. Okay. Also on the rover is our gamma ray and neutron spectrometer, LV-GRNS. The GRNS system will be used to map thorium abundance, and then also major elements like silicon, magnesium, and iron. And we have 2 detectors as part of the GRNS. We have a 2.5-inch diameter click detector that's sensitive to GRS or gamma rays, as well as epithermal neutrons. And then we have a 2-inch diameter click detector, which will give us the abilities to measure thermal and epithermal neutrons. And this system has heritage and draws from the mini neutron spectrometer on LunaMap. Now, on top of working on our instrument development as we proceed towards CDR in December of this year, we've also been working really hard to look at the wide range of orbital observations that we have of the Grooteisen domes and start picking our landing site. And so using the evaluation criteria that we see here on the left, we've identified a location on the Gamma Dome for our landing site. And so you can see here in the upper right, we see this green box, and this green box near the edge is highlighting this zoomed in perspective view of the area that we're most interested in. Now, when we were picking our landing site, we really wanted to focus on areas where we would have access to boulders and regolith because we want to study both in situ. And when we looked across the dome, this approximately 200-meter fresh crater was ideal for that because we can see a large boulder field that has been exposed. And so the landing site that we're looking at is on this bench or plateau that is just again on the edge and will give us access to the debris field from that small impact crater. We've used our range of data sets to characterize all of the hazards in the area and to pick a landing ellipse that minimizes those hazards. And so here what we're showing is our selected landing ellipse. The center is our landing site, and I'm highlighting everything that we've considered a hazard. So these are slopes greater than 10 degrees, terrain ruggedness index over 0.4, and then also all the boulders and craters that we can image, at least to our eye in LROC NAC data. Okay. And so on the next thing that we are looking at is actually identifying where we want waypoints to be for our rover traverse. And so we've been using maps of our expected line of sight between our landing site, which we can see in the X, and then in the rover, which is this area that we've highlighted in green. And so we've been looking for areas where we want to go and really accomplish our key investigation goals. And I should note that from this location, we can also see the Mare below, and depending upon where the peregrine lander lands, we may get images of the surrounding Mare for the peregrine lander. And with that, I will leave my summary slide here, and thank you for your time.